So I'm actually very happy that Wilfred spent some time talking about some of the things that he did, because I think you'll be seeing very similar themes in the talk that I'll be saying here as well. I should also mention that the work that I'm going to be describing here is largely facilitated by the Center for E3S, and is actually largely done by a former student that was co-advised by Sujay King and myself, Hey Cam, as well as a current graduate student, Yue Liu. So to give you a little bit of context, what I'm hoping to do with this particular talk is say a little bit about what is it that I think really at the circuit and system level sets the requirements for a lot of these new and alternative devices that Wilfred and others will be talking about, or Wilfred already mentioned and others will be talking about throughout the rest of the next couple of days. So before I do that, this is, I'm sure, sort of very obvious to everyone, but I did want to give you a little bit of a reminder as to why we're here in the first place. And I think the reason we're even having this symposium is really that indeed CMOS basically hit this power wall. So depending upon which company you talk to, they either call this sort of a right-hand turn or this power wall. This is, let's say, Intel versus IBM speak. But nonetheless, the basic idea is very simple, which is that with our current CMOS transistors, essentially the VDD and the threshold that we can use is really limited by the Boltzmann constant, temperature, and electronic charge. Right, so that basically says there's not really a whole lot you can do about it, except for some of the effects that we will talk about later on in terms of short channel variability and things like that. So it is certainly true that power is a very big concern, very big issue, but I did want to remind everybody that at the end of the day, what this is really all about is actually delivering more performance or more functionality for the same or lower cost. Okay? So the reason I want to make that reminder is because in order for me to sort of say a little bit about what I think are the requirements on the devices themselves, I have to make some assumptions about what the systems will actually look like. And it turns out that I think most of the assumptions that I'm making are really implied by this cost factor. Okay? So the first assumption I'm going to make is that I'm going to stick with binary digital logic. Okay? So the reason I say that is not because that there isn't very interesting things you can do with, for example, neuromorphic and other kinds of architectures. It's simply because in the general purpose context, I believe it's going to be the case that replacing the entire stack of design and software we have on top of everything that we've built today will simply be too expensive to justify the investment. Okay? So given that I'm sticking with binary digital logic, that of course implies that the devices need to have some kind of gain, or really more appropriately noise margins, right? Because that's, after all, what digital logic means in the first place. The second assumption I'm going to make, which perhaps in some circles will be a little bit controversial, is that I'm going to assume that whatever this new device is has yield and reliability comparable to CMOS. Okay? So again, there's certainly lots of very interesting work that can be done in variation or stochastic kinds of processing. But nonetheless, I think the investment to get those things to really work in a general purpose application is, again, so high that simply it'll be very difficult to really see how that will have a big impact, at least in the general purpose space. Perhaps the accelerators, I think that's a very interesting thing to look at. But again, general purpose, we really are going to need to have things comparable to what we have in CMOS. Now, it is true that CMOS reliability and yield, or I should say really reliability and variability, tend to get worse as we scale technology, but we shouldn't make that any worse with these new devices. And of course, just to give everybody sort of a heads up, that means we need about 5 billion devices or so per chip to last about 5 years. Okay, that's kind of about where we need to be. Of course, at the end of the day, if we make all of these assumptions, then it means that we are indeed looking for new devices that have, at the circuit or system level, lower energy over some range of performance and area. And there's certainly an intimate trade-off between both of those. And of course, at the end of the day, we can translate all of these metrics back to just real dollars of what is the functionality I'm selling you for what cost. Okay? So in order to actually come up with some of these requirements on the devices, we do have to say a little bit as to what the digital chips that are using these devices really look like. This is really going to be focusing mostly on the processing side of the world. There are indeed many other issues as well, but this is clearly one of the biggest ones in several of the application spaces. So of course, if we look inside of a processor, there's probably as much variation in terms of what the processors themselves are dissipating as there was even in sort of the server or blade level. But nonetheless, if we look at typical numbers, basically the most important thing to realize is that a large chunk of the power, if not is exactly taken by the logic itself, but at least should reasonably track with the characteristics of the logic. So that means that as long as we realize that basically the performance or the clock frequency we get is essentially set by the delay through that digital logic, then if we can come up with a fairly simple model for what that system looks like and how we can trade off between supply voltage, threshold voltage, performance, energy, and area, then we should have actually a pretty reasonable understanding of what the entire rest of the chip should look like. So if we're going to do that, then nicely enough, modeling logic is actually quite easy. We can basically just say, look, what we're really going to have is two flip-flops that essentially set the synchronous or the length of that cycle, and essentially a bunch of, let's say, logic gates in between. And if I'm going to model logic gates, I can just say, well, basically they look like inverters. Okay, that's not to say that, of course, a real chip is just a pile of inverters, although actually, if you paid close attention, there's so many repeaters in there that, if you really counted what was the number one gate, it probably would be an inverter. But nonetheless, there is indeed real logic happening somewhere in the chip, but inverters are a very good model for that logic as well. Okay? So if we look at this, then there's really only sort of a few parameters that actually end up setting our overall energy and performance. The first is the so-called activity factor, which is just how often do essentially the logic signals in that chain, how often do they transition on a per cycle basis. Okay? There's also the so-called fan out, which is basically just how many other logic gates each individual logic gate drives. There's, of course, how much capacitance each one of these gates has. And there's the so-called logic depth, which is how many stages of logic do you go through from one flip-flop to the next. Okay? So if we use this very simple model, it's actually very easy to come up with essentially what the delay of the whole chain would be, which of course sets the performance, what the total energy of that whole thing would be. It's too early in the morning for me to walk through a bunch of equations, but for those who are interested, feel free. It's nothing too complicated. And if we do that, we can actually sort of do some simple math and just come up with the total energy is this expression that I'm giving you here down on the bottom. Now, the only thing that I did want to point out is first to just reemphasize there's this VDD squared here. So of course that is indeed the big hammer in terms of trying to lower the energy per operation. But you'll also notice that there's kind of this trade-off between the on over off current ratio of the device itself, where on current means just, when you put it at the full supply, try and turn it on, how much current you get. Off means when you're actually literally trying to make it as dead as you can be, how much leakage current you get. You'll notice that there's this trade-off between the on-off current ratio and essentially this, let's say, system or circuit level parameter, which is the logic depth times the fan out divided by that activity factor. Okay? The reason I want to point this out is that once we actually really start looking at what we have to do with the devices, usually it's this on over off current ratio that's kind of the number one constraint. Okay? And so what you'll notice is that at the end of the day, what I really should be doing is I shouldn't just tell you the on over off current is X. You should actually do an optimization, right? Where you try and figure out what is really the best VDD, VTH, and everything else that I can pick for my device to actually minimize the energy I want given a certain performance target. Okay? And in other words, by changing these, I'll actually be modifying that on over off current ratio. Okay? So in order to do this, I do have to assume, of course, that I can actually change the threshold one way or another, either by doping or changing work function or something like that. But for now, let's assume that that is indeed the case. So it turns out that if you do this optimization in CMOS, at least for, let's say, the strong inversion operating region, and this is actually work that was done by Nose and Professor Sakurai, who nicely enough is sitting here in the audience, what they actually found was that the optimal on over off current ratio is indeed just proportional to this logic depth times the fan out divided by the activity factor. And if you just kind of glance back at this thing here, again, that kind of makes sense because that's really the only thing inside of here that I on over I off is trading off against. Okay? So interestingly enough, it turns out that that result is not actually very sensitive to what device you use. Okay? So in fact, even if you stick with CMOS and you move through all the different operating regions, or you move to something like a TFET or a carbon nanotube or any one of the other very strange devices people are talking about, you can actually show that this general form of the optimal on-off ratio being really proportional to that logic depth fan out divided by alpha really basically is fairly universally true. Okay, so this is actually some work that Hey Cam and Sujay King and myself have done and will be published shortly in the Transactions on Electron Devices. It tells you sort of the exact real form of things. Tells you that things really depend somewhat on this local subthreshold slope, somewhat on the local slope in the on state, and somewhat on what this sort of global slope is. But nonetheless, the final general message is indeed you can very easily predict what the on-off current ratio needs to be simply by looking at these circuit level parameters, even without knowing too much about the devices themselves. So given that that's the case, given that we can actually say something about what this requirement will be, let's actually go through and run some numbers and see what it tells us. Okay? So typical logic depths are order 20 to 40 or so. And they're kind of stuck at this point because if you try and go too much smaller than that, basically the overheads you pay for those flip-flops pretty much quickly kill you. Okay? So this turns out, and this has actually been shown by several different works, both IBM and some in academia, this is kind of about the right place to be sitting at. Activity factor-wise, and this is perhaps surprising to many people when you first see it, but activity factors, typical numbers are really in the order of 1% to around 0.01% or so. And if you sort of think about this from an intuitive standpoint, in any sort of complex logic circuit, it's going to be the case that most of the outputs don't change on any one given cycle. And that's really why you end up with these such low activity factor numbers there. Fan-outs are kind of order 2 to 6 or so. Again, there's some pretty simple reasons why that turns out to be. And so if you just take all these numbers together, the optimal on-off current ratio ends up being something like 10 to the 4 to 10 to the 6. Okay? Now, I did want to sort of make sure one thing is very clear, because sometimes people look at this number and say, oh, but this is horrible, it's really high, are you sure, can't we get away with something much smaller than this and just do power gating or something like that? Well, unfortunately, the answer is no. Okay? So this is really the logic switch requirement. Okay? So it turns out that whatever power management we're doing really will not change this number. So to clarify that, I wanted to just sort of walk through a simple thought experiment. Okay? So the whole idea of power gating is basically saying, okay, look, why don't I just put another switch in series with my power supply so that when the logic is not doing anything, I basically just turn off the power, right? And hopefully that should give me lower leakage as long as I have another switch here that has a good, essentially, on-off current ratio, right? So that all sounds great. And indeed, this is actually utilized very heavily. But we have to realize how it's utilized, or rather why it's utilized, okay? So let's try and push this to the limit. Let's say that we put a power gate in series with each and every single one of our logic devices. Okay? Well, if you think about it, that basically means that the only way you'd know whether or not to turn this power gate on or off is based on the logic itself. Okay? So in other words, all you're really doing is using that power gate switch as a part of the logic. In other words, you're basically just building your logic out of that switch. So if that switch is no better than your normal switch, or if it's slower or has some other undesirable characteristic, sorry, that's the characteristic you have for your logic. Okay? So what power gating is really actually good for is simply eliminating or reducing the leakage power when the system is actually off. And what I really mean by that is when it's really obvious that you're not doing any work, and by obvious I mean the OS knows you're not doing anything, or the chip can very easily detect that it's not doing anything, that's really when power gating is useful, right? Because there, it doesn't really cost you anything to decide, oh yeah, I'm not doing anything, so I really should remove all that power consumption from the leakage, right? If I don't really know, then basically I have to actually compute whether or not I'm doing that, and that generally involves actually just redoing the logic in the first place, okay? So again, really the key point here is that all power gating is really doing is reducing the variability penalty at the system level, where that variability is just in core states like, are you doing something, or are you not doing something, okay? And that's kind of what this curve here is saying, is that if I had a system that was always on, this would be the energy delay curve I would get. If I had a bursty computation where I wasn't really doing things for long periods of time, that's sort of the energy performance I would get. If I reuse the power gating and I really know exactly when those bursts of computation are happening, that's how I would come back to this original curve. So, as I said, power gating is really just a mechanism of dealing with this system-level variability. But, of course, as was mentioned earlier, we need to also think a bit about the device variability. So, from a device variability standpoint, and as is typical for many of these things, it's usually the threshold variability that hurts you the most. It really actually impacts you in essentially two ways. So, the first way, which is actually somewhat more mild, is that if you've got this complex chip with billions of transistors and hundreds, if not even thousands of critical paths, then unfortunately, because of variability, some of the transistors on those critical paths will be slower than what you expected. And so that means that's kind of equivalent of saying that the ion you're going to get is not really going to be the nominal ion. It's going to be some sort of degraded ion due to variability. What's unfortunately actually much worse is that from a leakage standpoint, once you throw in threshold variability, your leakage will be much, much higher than you originally expected. And the reason for that is that you've basically, again, got billions of these transistors sitting around doing nothing. And unfortunately, some statistically significant percentage of them have lower threshold voltage. Well, if they've got lower threshold voltage, that means they have exponentially more leakage. So your overall leakage in the chip is really dominated by those devices that, statistically speaking, have that lower threshold voltage. Okay? So not only do you basically get sort of a lower I on, but you actually get sort of exponentially larger I off. Okay? So that basically means that as you start increasing that variability, you have to increase both the supply voltage and the threshold voltage to maintain that same original optimal I on over I off. Okay? And as you can imagine, increasing both the supply and the threshold always means you're dissipating more energy per operation. Now, in the context of, again, I think the rest of the discussions we're going to be having here about these new and more aggressive, more steep devices, unfortunately, this has a very important implication, which is that if I really go and I give you a very steep device, but I still give you the same, X millivolts of variability, unfortunately, the answer is that you've actually done me a disservice. Okay? Because if you have a super steep curve and you have the same number of millivolts of variation, guess what? You've exponentially amplified how much leakage all of those off devices are going to be giving you. Okay? So in fact, as I said before, for a certain level of variability, for example, let's say I had 40 millivolts of sigma VTH, and I did, I did a really excellent job. I came up with a 15 millivolt per decade nominal device. Guess what? You're actually, your effective subthreshold slope is something like 120 millivolts. In other words, you're worse by almost a factor of 2 from what CMOS could have done. Okay? So the point of this is not to say, it's all doom and gloom. It's only to say that if we really start thinking about these new devices, we have to consider that, actually not just consider, quantify the device variability very early on in the process. Because if we come up with, these really cool ideas that seem like they give us incredibly sharp slopes, but fundamentally have very large variability in them, it's pretty clear that they won't really work in a system context. They won't really bias anything. So the last sort of issue that I did want to mention, which was touched upon earlier, is this question about basically what happens with those wires. So there's indeed quite a bit of focus and attention that's paid to essentially explicit wires in the system. So things like these big buses and communication networks. But it turns out that actually even just those local wires play a very important role. And to kind of motivate why that's the case, I think it's just the simplest way to realize that is to just look at what are the actual capacitances you can get from realistic sort of devices and wires these days. So if I go and I just try and build the smallest device that I can, typically I'm going to get something on the order of about 0.1 femtofarads of intrinsic device capacitance. You'll notice I didn't quote a technology here because it turns out that for variability reasons, that number has not been scaling very much. But there's maybe a factor of 2 or so that you could wiggle around there. Well, if I just have about 1 micron of wire, which, okay, granted, 20 nanometer technology, that's a reasonable number of gates. But still, we're not talking hundreds of gates. We're talking 5-ish. That's already 0.2 femtofarads of capacitance. Okay? So that's already telling you that even for these very, very short wires, both your energy and your performance are really being dominated by that wire capacitance, and not really by intrinsically the characteristics of the devices itself. So in fact, it turns out that just the fact that these wires exist and that unfortunately the capacitance you get from them, there's not a whole lot you can do about it, that's what often sets the sort of required device conductance. And by conductance, I just mean essentially the sort of supply voltage divided by the on current. Okay? And so when you're moving performance around, it's basically this device conductance that you're playing with. Okay, so having said all of that, I did want to say a little bit about where, at least in my opinion, a lot of these new devices really look good. So I think the main sort of data that I've seen so far seems to indicate that, unfortunately, for better or for worse, it seems to be really, really hard to get both a sharp subthreshold slope and actually low on resistance in that high performance end of the curve. Okay? So that basically means that you are indeed going to be sort of stuck with this trade-off where either you're looking at these so-called low voltage devices, something, for example, like a TFET, or you're maybe looking at these, let's say, better high performance devices, for example, something like the carbon nanotube FET. Okay? So that initially sounds like somewhat bad news, but I think there is still a sort of light at the end of the tunnel here, which is very much related to what was mentioned earlier, which is that even if indeed we're only able to get these devices that have lower, basically better subthreshold slope, and therefore look good in this quote-unquote low performance end of the curve, they are indeed still useful in the parallel context. Okay? And indeed, this is really where a lot of the improvements in energy efficiency have been coming from over the last probably 6 or 7 years ago, is really by relying on parallelism as heavily as we can. Now, that's not to say that parallelism works everywhere. There are indeed applications where you need the single thread performance. But to the extent that you can, you will try and push into this parallel regime, simply because that is really the only big hammer that we have to really get much more energy efficient hardware. So from that standpoint, I think there is sort of another, let's say, somewhat good news from the standpoint of if you're working on new devices and trying to get them to be useful, which is that for better or for worse, in CMOS, there is a limit as to how far we can go in parallelism. Okay? So there's actually the area limit that was mentioned earlier, but in fact, even if we were to willing to spend as much area as we wanted, even from an energy standpoint, there's a limit on how far you can go. And that's simply because CMOS has a minimum energy per operation. Right? And remember, the whole trick with parallelism is that you were doing this simply because if you backed off on the per core throughput, it brought you a more efficient operation. Well, if I hit a minimum energy per op, hey, I can put as much parallel stuff as I want, doesn't buy you anything. Right? And so basically, once I'm at that minimum energy, that sort of sets the minimum supply voltage I need, or actually I should say it's set by the minimum supply you need to achieve the optimal ion over I off. Once you're there, basically game over. Okay? So I would claim that this is probably the likely opportunity for these new devices. Once we start really getting close to this region of the curve, where things just sort of flatten out very, very quickly, then if we really can come up with a device that, for example, gives you now this extra factor of a few, let's say 10x or so, down in that energy, that's where you really may have a great opportunity to make an impact. Now, of course, having said that, this is only if you can actually achieve that ion over I off I mentioned before, and really get something like about a factor of 10 improvement in the active power. Because, hey, if it's less than a factor of 10, by the time we're done, it probably won't really be all that much better. Okay? So just to briefly summarize and hopefully leave some time for questions, what I hope to have sort of given you as a take-home message is that we can actually use fairly simple circuit and system models to at least come up with the basic device requirements. And again, the two key points there are really that this ion over I off are simply set basically by the logic depth and the activity factor. And that we really do have to consider both variability and even these very local short wires kind of from the first order when we're really looking at these new devices. Because there's lots of games you can play in the device that make it have much smaller capacitance but still reasonable electrostatic control. At the end of the day, it wouldn't really actually help simply because of the wire capacitance. Okay? The other key point is that parallelism really is limited by the device's minimum energy per operation. And so, at least again in my opinion, I think this is really where the opportunity for a lot of these new devices are. So for example, the TFET, I think, is an interesting device simply because it gets you to this lower energy per operation. So the final plug that I did want to make is that, and although I didn't speak about it too much explicitly here, is that I think the device and circuit code design is really going to be quite critical. And that's going to be especially true if whatever new logic device you're talking about has very or even slightly different characteristics from CMOS. Because as you can imagine, if we just take that device and plug it directly into our current infrastructure, that's not going to be really the right way of using things. There may be quite a few optimizations we can make to substantially either leverage the advantages or really mitigate the disadvantages of whatever these new technologies are. So with that, I'd just like to thank a few of the funding sources, particularly the NSF Center for E3S, and thank you all for your attention.
Okay, we have time for a few questions. Yeah.
Just one question. I know you talked about optimizing ion over ion, right? Why not look at L and alpha, activity and logic depth? Because at the end, it's that whole ratio, right? I believe.
Yeah, that's correct. So the thing with logic depth is, as I mentioned before, there's not really a ton of wiggle room there. Simply because if you start really trying to push that down, which is the direction you'd like to go to deal with less ion over I off, or to get less ion over I off, basically the overheads from the clocking elements really kill you very quickly. In terms of the activity factors, it's kind of an interesting question. there may be some games you can play to sort of reorganize the logic and things like that. But generally speaking, there's not really a whole lot you can do once you've really sort of gotten to the quote-unquote right logic topology in the first place. So this is not to say that there is no wiggle room there whatsoever. But I'd say that from a sort of order of magnitude standpoint, I'd stand by my original statement.
So both you and Wilfred Hensch told us that TFET devices would be good if we went slow, but they would not perform and give you the very high-speed performance. And I think that comes from the idea that the on-state current is not that good from TFET. But already we're starting to see indications that in some of these type 3 band alignment switches that we can get a very, very high current, or at least high enough to be competitive. And so is there any fundamental reason why the TFET cannot also compete for high performance as well?
No, so I mean, if indeed you really can get the, comparable conductance densities, then absolutely, that's an interesting solution. Most of the data that I've seen so far, and I grant you I'm not the expert, you're much more the expert on that, has not indicated that there's yet a great, sort of proof of that happening. But, absolutely, if you get a better device, then we'll be happy to use the better device everywhere, right? There's no question about that.
Yeah, so I think there's some indications.
Yeah, so maybe I would maybe rephrase it a little bit differently in that, with enough development you can probably get there. There's probably ways to do it. But I think what will actually drive you to getting into it in the first place will be the advantage you have in that energy efficient part of the curve. And Wilfred here, I think, has more.
Yeah, I think 3 things have to be shown, right? First thing is that you have to maintain the on-off ratio in this neighborhood, what he said.
Right.
Second, you have to come to at least 30% of the on-currents that the CMOS technology has, right? And the third point is that whole thing has to work at a 0.5 volts. And there's no indication that all these 3 things are fulfilled with the tunnel FET yet.
Well, I agree. I would only criticize 0.5 volts is not a very ambitious goal. We should aim for a much higher goal, especially at this conference.
This would be nice.
Yeah, no, so just to reemphasize a little bit. Just to reemphasize a little bit, I think if you look historically, right, CMOS was also viewed as the slow dog compared to BJTs, right? And nonetheless, it won not because it was the high-performance technology initially, but because it brought you the energy efficiency. And so I think if we really focus on knocking down that voltage, making the device more energy efficient, that'll give us however much time we have left in the whole scaling curve to actually work on bringing the performance side of it back. That's sort of my personal opinion.
Okay, last question.
Yes, I'm interested in your comment about that the stick device is vulnerable to the variability in threshold voltage. And then later you mentioned the parallel is a big hammer that we could use.
Mm-hmm.
So, but for parallel you will need more devices, right? So does that make it much difficult to?
I see. No, it's a good question. So there's a couple of things to keep in mind there.
Can you rephrase the question?
Yes, so the question was basically saying, look, we said that variability was a big issue with these steep devices, but we also said that the way we're going to use them is by going to a larger parallelism, which potentially means that we're actually using more and more devices. So I think there's a couple things to keep in mind. Generally speaking, when we move to that parallelism, you also will redesign the cores a little bit. So you may end up using exactly the same core in this high performance space as you are in the parallel case. So that does save you a little bit of devices. Having said that, however, your question is an excellent one in that it basically says, look, we really have to meet essentially some level of variability at the device level, because if we don't, I just won't be able to use the device in the way I want it. Now, the statistics of this leakage thing work out that basically the sort of average leakage you get is not really dependent upon the number of devices once you're more than, say, 1 million or 100 million devices, because it's really only sort of, you're dominated by the things that are statistically significant. But nonetheless, it does go back to, I think, one of the points I made earlier, which is, I think for any of these to be reasonably interesting, they have to meet sort of yield and reliability considerations very similar to what we have today, or what we would need to have in a future CMOS technology, so that we can indeed build the number of devices we'd like to build to get to those parallel solutions. So it's an excellent question. Yeah?
For the very slow device, really comparatively slow devices, you can make it up by parallelism, right? Given what Wilfred just said about area per bit, where's it go? Where's the trade-off?
Yeah, so the way I would basically phrase that is just to say, and I think I'll just go to this curve here, it's basically saying, as with any other engineering curve, it basically says, look, if I'm in CMOS and I'm at this part of the curve, you really don't want to go any further, right? Because you're getting incrementally almost zero benefit and paying huge cost for it on another axis, right? So that's actually, this curve is sort of showing something interesting in that if indeed you get this new device to cross over kind of right at the point where CMOS is really running out of steam, right, that's where things will be interesting, right? Because you won't be paying this enormous benefit in performance and therefore in area to actually get back some of that energy efficiency, right? So I'd basically say that if you really can get something that looks like this, and you can show that it's scalable so that you can continue to actually pack more of these devices in, continue riding on this curve with more parallelism as you go to new technologies, meaning new lithographic technologies, then that's sort of the opportunity. But it does say, if you've just got a device that's 1,000x slower, somewhere off over here, where we'd need, n nodes of technology scaling just to make it even competitive from an area standpoint, then again, that's really not a viable solution. It's a good question.
Okay, in the interest of time, we need to move now.
Yes, no, thank you.
Okay. Let's thank the speaker again.